Hello and welcome to our last installment of Electrochem. We're going to take a look at self-stoic, the best kind of stoic. I know, I'm a nerd. Anyhow, in today's installment, we're going to be taking a look at how we use stoichiometry and half reactions to look at the molar ratio between the number of electrons, and the entities. Okay, so oxidation and reduction half reactions allow us to establish molar ratios for ions, elements, and electrons. Take a look at this half reaction. We'll notice that there's one zinc ion. Compare that to 2 electrons in the reactants part of the half equation, and your zinc metal that's being formed. And you'll notice that if there's no coefficient in front of an entity, it's a 1, right? Here's our coefficient of 2, and here we have a coefficient of 1. And it's kind of like saying it's a 1 to 2 to 1 ratio. And we use these ratios to go from electrons to the amount of zinc that's being produced. And if I'm producing the amount of this amount of zinc solid, for example, how many electrons are being produced? And anytime we're talking about number of electrons or the amount of electrons, we're talking about the moles of electrons. And how much zinc, for example, is required in order for that to happen. A lot of fun stuff today, kiddos. And it's not a long PowerPoint, it's not a long podcast, but just a different type of thing and something new, right? So why not? It's another day, something new. Here's a cool formula. Q is equal to IT. Q is the charge, which is in coulombs, and it's the unit of electrical charge, and it's referring to the electrons, kiddos. And I is current, which is measured in amps, but more importantly, we also know that an amp, because of the formula, if we manipulate the formula, 1 amp is equal to 1 coulomb per second. So 1 coulomb is the quantity of charge transferred by a current of 1 amp during a time of 1 second. So clearly, time is measured in seconds. We have current, which is an I in the formula, and the units are amps, and the word is current. Nothing matches, but why make any kind of sense? And 1 amp is equal to 1 coulomb per second. Good times. Time is in seconds. That's simple. No complication there. And Q is the charge, and the charge is measured in coulombs. That's your unit. And yeah, good times. And that's a capital C, by the way. So let's take a look at Faraday's law. Faraday's law kind of helped us understand something called Faraday's constant. So Faraday's law states, and there's different types of Faraday's understanding, because in physics, Faraday comes into when we're talking about induction. But for chemistry, for our purposes, we're just looking at the Faraday constant. So the law states, in an electrolytic cell, the mass of an element produced or consumed at an electrode. So we know that at any particular electrode, you're either producing mass or you're breaking it down, is directly proportional to the time. So the more time that goes on, considering that there's a constant current, there's no change in current, the more time is allowed for this reaction to occur, either the more a metal is going to be produced at one of the electrodes, or the more the electrode is going to, one of the electrodes is going to break down and form ions. So it depends on which direction you're looking at, but that's okay. The molar charge of electrons, or the Faraday constant, is 9.65 times 10 to the power 4 coulombs for every mole of electron. Okay, that becomes really important when we compare this to our amps, which is our current, which is measured in coulombs per second. Okay, so we're going to see how they kind of relate to each other. So here's a problem. The technology of the Hall-Héroult cell for producing aluminum. So this is a cell used to produce aluminum, because sometimes we want to produce a metal from its ore, okay? Has improved considerably since the first industrial factory. Modern electrolytic cells may use up to 300 kiloamps, but remember, anytime you're using that formula, kiloamps have to be converted to amps. 300 kiloamps of current. What is the charge that passes through one of these cells in 24 hours? Okay, so that's our data that we know. So it's really important that you list what you know and what the heck is going on. We're given time in 24 hours. That is not useful to us, kiddos. We need to convert to seconds. And we know that 1 minute is equal to 60 seconds, right? And 1 hour is equal to 3,600 seconds. Oops. and we need to convert to 24 hours. So you know what to do with that. 300 kiloamps has to be converted to amps, so we have to multiply by 1,000 and to get 300,000 amps. And we're looking for a Q. Okay, which is the units are coulombs. So here we have our conversion to seconds. We have our formula. Always write down your formula. Q is equal to I over T. Okay, we have our time. And I always like to start my equation with the one piece of evidence or one piece of data that has only one unit so that it's easy for me to cancel those units out, right? So for me, I would switch these around just because it makes sense to me more. This hurts my brain. What I would like to do is I would like to start with 8.6 times 10 to the power of 4 seconds, and then multiply that by my amps, which is 300 times 10 to the power of 3 coulombs per second, which is equal to 1 amp, right, kiddos? And now my seconds cancel out, and I get my answer in coulombs. This just makes more sense. The book does things backwards. It hurts me, but that's fine. The book can't be perfect, right? So what amount is another example? What amount of electrons? Now, here we go. Anytime you hear the word electrons, anytime you're either being asked for electrons or electrons is the amount of electrons is given to you, always go to Faraday's constant. You always just write it down because you're going to use it. So what amount of electrons, and you know when we're talking about amount, we're talking about moles. That is a given. What amount of electrons is transferred in a cell that operates for 1.25 hours? We know we're going to convert that to seconds. At a current of 0.150 amps, and we know that we also know that that is equal to 0.150 coulombs per second. Okay, so here we are changing it, the time to seconds. Again, this hurts my brain. What I prefer is, I'll write it down here, 4.50 times 10 to the power of 3 seconds. Now I'm going to multiply that by my amps, right? But my amps, I'm not going to think about it amps, I'm going to think of it as coulombs per second. So 0.150 coulombs per second. Now I can see that these guys cancel out in a much more efficient way. And now I'm also going to include Faraday's constant. Now what I want to do, kiddos, I want to make sure that my coulombs cancel out. So I'm going to take this and use it so that the coulombs are on the bottom and my moles are on top. So 1 mole over 9.65 times 10 to the power of 4 coulombs. This time my coulombs cancel out and I'm left with an answer in moles, which is equal to 6.99 times 10 to the power of negative 3 moles. Or if I multiply that by 1,000, I can get the amount of millimoles. So convert, here's another example, convert a current of 1.74 amps. So this is what I know. I'm given some information. For 10 minutes, I have to change that to seconds, to the amount of electrons. What do we do? Faraday, because we're mentioning electrons. So remember, convert time to seconds. Use 1 amp is equal to 1 coulomb per second, and electrons, Faraday's constant. So here's my time, and here's the textbook dumbness. 600 seconds times my amps, right? 1.74 coulombs per second. So my seconds cancel out. Now I want my answer to be the amount, which is moles of electrons, okay? So now I want my coulombs to cancel out. So 9.65 times 10 to the power 4 coulombs, and that's for 1 mole of electrons. Okay, kiddos? So then what I'm going to do is I can see very clearly my coulombs cancel out, and I get my answer in moles of electrons, which is 0.0108. That's your answer. So let's move on some more. How long in minutes? Now we're looking for time. So we're going to identify the fact that we're looking for time. Keep in mind in the questions asking for time in minutes, you are going to get an answer in seconds and then convert to minutes. How long in minutes will it take we'll take a current of 3.50 amps or 3.50 coulombs per second to transfer 0.100 moles of electrons. Now I have my moles of electrons, and I need my Faraday's constant. This time I'm converting my moles to coulombs. So the book got it right. Yay. I'm going to start with my one entity that has only one unit because that makes total sense. 0.100 moles. This time I'm going to multiply by 9.65 times 10 to the power 4 coulombs per mole because I want my moles to cancel out, right? Now I have my answer in coulombs, and now I'm going to use my amps, my understanding of amps, and flip it around so that my coulombs cancel out. So instead of saying 3.50 coulombs per second, we can say 1 second has 3.50 coulombs in this particular case. I'm using that so that my coulombs cancel out and I get my answer in seconds. This time, instead of multiplying by 60, I'm going to divide by 60 to get my answer in minutes. 46.0 minutes. Okay, half-cell calculations. Separate calculations are carried out for each electrode, obviously, although the same charge and therefore the same amount of electrons passes through each electrode in a cell or a group of cells in series. So even though the same amount of electrons passes through, we have different half reactions at each electrode. So let's take a look at what is happening on each half of this half reaction. Okay, this is the Stoich that we love. This looks familiar. What is the mass of copper? So that is what we're looking for. So it's very important. This is the most important step, kiddos. I want you to populate that half reaction. I am asking to find my mass of copper. Anytime you have mass of anything, you always have to have your molar mass. Okay, and it's in grams per mole. So that's very important that you include your units. Yeah, okay, so what is the mass of copper deposited at the cathode of a copper refining cell operated at 12 amps for 40 minutes? So this stuff with the amps and the minutes and all that, that is applying to the side of your electrons, okay? So we have 12.0 amps or 12 coulombs per second. The time is 40 minutes. I'm going to multiply that by 60 to have a time of 2,400 seconds. And Faraday's constant is 9.65 times 10 to the power 4 coulombs per electron. And all this stuff like your coulombs and your seconds really has to do with this half. In particular, it has to do with the electrons, okay? So now that we have our information, let's do what we have to do in order to get to your mass. All right, we're going to start with the stuff over here. Now, I'm going to start out. Now, think about this. I'm moving my way 2 moles of electrons to then get my mass of the copper, right? Because once I have my moles of electron, I just use my molar ratio to go from this entity to this entity. So I have to start with seconds to get to my coulombs to then get to my moles. So here's my 2,400 seconds. Now, I have my amps, 12.0 amps, which is equal to 12.0 coulombs per second. Or it also equals 1 second generates 12.0 coulombs. I'm going to use this one here so that I cancel out my seconds. That's going to leave me with coulombs of electrons. I don't want coulombs, I want moles. So that's where Faraday's constant comes into play. This time I want my coulombs to be on the denominator so that my coulombs cancel out, and I'm left with moles of electrons. Now I'm here. I want to go from here to copper. So I have to use my molar ratio of what I have on the bottom and what I'm looking for on the top. I have 2 moles for every 1 mole of copper being formed. This is going to cancel out my moles of electrons. Now I have an answer in moles of copper. I don't want moles of copper, I want grams of copper, and that's where we use our molar mass. We use our molar mass to go from grams to moles and moles to grams. This time I want to go from moles to grams so that I cancel out my moles. Moles go on the bottom, my grams go on top, and I get an answer of 9.48 grams. And that's as hard as it gets. It doesn't get much harder than that. So I'm going to give you another example, but much quicker. Silver is deposited on objects. Remember with electroplating in that example of the spoon. So silver is deposited on objects in a silver electroplating cell. If, now this time, you're given the mass of the silver, if 0.175 grams of silver is to be deposited from a silver cyanide solution, And here's our time, 10 minutes. Remember, we're changing that to seconds. Predict the current required. So we're looking for amps, kiddos, or coulombs per second. Okay, cool. Let's break it down. Here's our time, and we're going to multiply that by 60. And we know that we are, anytime we're dealing with electrons, we are going to use Faraday's constant. On this side, we know that we've already produced 0.175 grams of silver, and here's our molar mass. I have to start on this side because there's no question marks on this side. There's a question mark here, okay? We always start on the side that has no question marks, all the data that we need. So this is going to get us to moles of silver, right? So we have our mass, which is nice that the book decided to start with the entity with the 1 unit. We use our molar mass to cancel out our grams. Now this is 1 mole of silver. So let's take a look at our half reaction. 1 mole of silver to 1 electron to 1 gram of silver. So it's 1 to 1 to 1. And that's where this ratio comes from, what I have over what I need. And that's going to get me moles of electrons. I definitely don't want moles of electrons. I would like, I want amps, right? So my moles cancel out and I get my coulombs of electrons. This time I have to convert my minutes to seconds. You don't have to use this in there. You can strictly go to here, which is 1 minute over, how many is it? 10 minutes times it by 60. And you just make sure it's 1 over your time in seconds. And the reason why it's 1 over the time in seconds, because I want to keep that coulombs per second, right? And that's going to get me 0.261 coulombs per second, or 0.261 amps, which is the same thing. And that's it, kiddos. Good old self-stoich. Have a great day, and we'll start the new unit soon. And have a great weekend.